All right. Oh, that's the wrong part. Let's go ahead and read this piece to your neighbor. Go. Story time. Cody, we're reading. Right, Milo, reading this piece.
Definition of wait,
Concavity.
concavity. On total interval line, concave upper line, wait, what?
So let me summarize what the definition of concavity is. Listen up. So if f prime is increasing, then the double prime is positive. Someone's talking over me. And if f prime is decreasing, then f double prime is negative. That sounds familiar from f to f single prime from last week. So when the function is concave up, so I want you to draw me a concave up graph. And our tangent line, no matter what, is always going to be underneath it. So meaning the graph lies above the tangent line. The concave up graph is above the tangent line. The second piece, if I make a concave down graph, let's make that one, then that graph, no matter what, when I make my tangent line, anywhere you want, is always below the tangent line. And that's pretty much proven by the picture alone, so I think that should be no problem. So let's look at the image and write out or highlight where we have concave up and down. And before I do, let's draw the arrow. The graphs go on forever. So would you guys agree this part is concave up? And right here, ever so slightly, it is concave down. I know it's like very little. So let's go ahead and put a dot where it's going to change concavity. And where you put the dot might differ only because this one is a quite broad one. Bless you. So with my green highlighter, I think I'm going to highlight wherever I see concave up, even if it's a slight bit like this one as well. And a different color would be nice. Concave down and concave down right here. So where it's changing concavity, it's called point of inflection that I'm going to abbreviate with POI. Again, POI stands for point of inflection. So we have another point of inflection right here. And then my third one. So let's go ahead and fill in the very bottom. At the very bottom, it says, determine the open intervals on which the graph of f of x is concave up or concave down. So let's write out concave up at the following intervals. So this is concaving up here and also another one. So let's write out negative infinity. What is the x value where the concave up piece ends? -2. And I have another spot, so let's go ahead and connect it with the union. 0 to what? 0 to 2. And then let's write out concave down for the next piece. What's our first interval? What to what number? -2 to 0, union, and then the next two? 2 to the infinity, very well. And our point of inflection is where the concavity changes. So POI at how many point of inflections do we label on the graph? 3 of them. And I want just the x values. What is the first x value? -2. Second x value? 0 and 2. All right, first page done. Okay, our next page. Let's read this piece to your neighbor.
CFC is a point of reflection on the graph of f, either f double prime is 0 or f double prime is undefined.
Yeah, that's part of 3.4, but it's theorem 3.8. Theorem's got its own numbers. Don't let that interchange and confuse you. All right, so to find the point of inflection, the bottom line is we need to worry about f double prime. When we found the critical numbers on last week for relative minimum and maximum, we did single prime. Today we're looking at double prime, but the rule still remains. When it's equal to 0 and when it's undefined, and specifically, undefined typically doesn't happen. When it does, it's normally when the x is in our denominator. Meaning when our denominator is equal to 0, it's going to be undefined, and we know that fact. So let's do an example right underneath it. So Xavier, let's read the instruction on example number 1.
Determine the points of inflection and discuss the concavity of the graph of f of x equals x to 4 minus 4x.
So to find the point of inflection, how many times do I need to find the derivative? Twice. So let's find f prime of x. What is the derivative of x to the 4? 4x cubed. How about our next piece? Minus 12x squared. And then let's derive this one more time for the point of inflection. What's our derivative of the first term? 12x squared. Second term? Minus 24x. So now I need to go ahead and set this equal to 0. What is our GCF that I could take out? 12x. And then I have remaining x minus 2. So the way we're going to list for the point of inflection, it's not critical numbers anymore because it's not relative extrema. Let's go ahead and write out P, POI. The first P stands for the possible point of inflection, meaning it could or could not be. So the first possible point of inflection, when I set this equal to 0, is x equals 0. Second one, x equals what number? 2. Let's make our number line. And we have no restriction on our domain, so negative and positive infinity. 0 and 2. And let's test out some numbers. And notice this is double prime, and that's just the graph of the original. What numbers should we test on the left? Good, -1. How about the middle? 1. To the right? 3. And when you are testing the point, it is the easiest with the factor form. Yes, you can go back to the original double prime, but for me, that will make my life miserable. So let's go ahead and put in our parentheses. When I plug in the negative into my first factor, is it a positive or negative? And when I plug in that -1 to my second factor, we get negative. So we know the result is positive. So the way we're going to notate this, it is positive, meaning cave up. And then let's go to the 1. When I plug in the 1 into my first and second one, the first one is positive, bless you. Second one is negative, so our result is negative, cave down. And then let's plug in the 3. They're both going to give me what? Positive. So point of inflection happens where the concavity changes. So in this case, and let's actually graph this. What the graph actually looks like, and I don't want to graph it in here, I'm going to do it up here. The graph is actually doing this, and our point of inflection is where the concavity is changing, and those two numbers are 0 and 2, in case you want to know the original graph. So we have point of inflection at, how many points of inflections do I have here? 2. The first one is at 0. Second one is at 2. And of course, because it's very important, f prime changes signs. Cody, did you write that down? The last piece? Write it, please. And then let's do the concavity. The function is concave up at the following interval. We have 2 pieces where it's concave up, -infinity to 0, union, 2 to the infinity. And we know that because f double prime is what kind of sign? Positive. Very good. Can we mimic that for concave down? Yeah? And how many locations do I have concave down? Just 1, 0 to 2. And that is because f double prime is negative. So now I think it's a good time for our card. So if you have to get a brand new card, that's fine. If you want to write this somewhere on your notes, that is also okay. We're going to add on to this card throughout the remaining of Unit 3. So here's what I want. I want you to leave some room on the margin because we're going to add on to it, but not today. I also want you to leave a little room next to the F's, but not today though, okay? So we'll add on to them sometime later. And I'm referring back to this card quite often from today and on. So when I go back to this and I have to wait on you to copy this over and over, that might not be nice. And go ahead and put 3.4a on the top right-hand corner for reference. So let's use this card to answer theorem 3.9. You guys about ready or a little more time? All right, let me know. Are we ready now? All right, so I want to go ahead and answer our theorem 3.9. Is everyone ready? Okay, if f double prime is greater than 0, doesn't that mean f double prime is positive? Positive. So let's go to our card. F double prime is positive. Then I know the original graph. When it's positive, the original graph has a relative minimum or maximum. What does that have? At the very bottom means there's a minimum. Boom. The next statement says, if f double prime is less than 0, that means it is negative. So when I go to this, when f double prime is negative, then the original graph has a relative maximum. And that is stated. That's why this card is really nice. All right? So I'm going to continue to use this on the next problem. For example number 2, it says to use a second derivative test. I kind of want to use the first derivative test and the second derivative test as a reminder. So let's go ahead and make a line right here. The left column is simply going to be a review from 3.2 or even 3.3. Or maybe I don't remember. All right, to find the relative extrema. So it's all about relative minimum and maximum. So let's kind of recap what we did last week. To find the relative minimum and maximum, to find the critical number, what did we do to our f of x? We found the derivative, and our derivative for this one is negative 15 x to the power of 4 plus 15x squared. And we set that one equal to 0 and factor out our GCF. I like to take out the negative, so our leading coefficient is a positive. That's just my preference. If you want to take it a positive, we'll get the exact same answer. Not a big deal. So I have x squared minus 1. So we have our critical numbers at this point. The first critical number, when I set the first one equal to 0, we get 0. How many critical numbers will the second one give me? 2 of them, plus or minus 1. So let's make our number line. And there was no limitation, so negative and positive infinity. We have our 3 critical numbers. In order is negative 1, 0, and 1. And we're comparing from f prime to the f. And I know we need to test out some points. Let's assume that we've already tested out the point because I don't want to waste time plugging things in. Just going to go ahead and tell you the first one is negative, second one is positive. The third one, I know we're anticipating it to be negative. This one is not well behaved. And I'm going to explain what that graph looks like in a little bit. So when it's negative for the f prime, the graph is going down. When it's positive, the graph is going up. This one is continuing to go up. Then I have it going down. So we know our relative minimum and maximum happens right here and right here, correct? So let's write out relative minimum is at x equals negative 1. And then where's our relative maximum? At x equals how many? Where is it increasing to decreasing? Positive 1. Here's what the actual graph looks like, and that's why there's two spots concurrently going up. And I'm going to graph it on here. The graph is going to go up and have a flat surface, continue to go up and come down. And if y'all remember me mentioning maybe saddle point, it might be part of it. But anyways, we found our relative minimum and maximum. This is simply review. Let's see how we can use the second derivative test. So the second derivative test we're going to use right here. The second derivative test states, find the second derivative, obviously. So let's do that. So we're going back to the first derivative. So we get our derivative of that is negative 60, how many? X cubed. And then plus how many x? 30? 30x? The second derivative test tells the following, and I'm going to go back to my card. If my second derivative is positive, then there's a relative minimum. If my second derivative is a negative, Sam, I'm up here, then there is a relative maximum. And that's only when you're plugging those critical numbers into our second derivative. So let's plug them in together. The numbers still remain f double prime of negative 1. Then I have f double prime of 0 and f double prime of 1. And yes, we're plugging it back into the second derivative that we found. And I know it's quite tedious, but bear with me. And then the 0. And then the 1. There we go. Now on here, what that exact number is doesn't matter. The bottom line is my n value positive or negative? Just by looking at this, is my n value positive or negative? Is it negative? What if I tell you this is going to produce a negative number times another negative is going to be a bigger positive? So we know this is a positive. So if it's a positive, the graph is going to concave up. What is this called in our original graph? That is a relative minimum. And the number I plugged in was negative 1, and that value does not change from the first derivative or second derivative test. Now let's plug in the 0. This one is not going to be a positive or negative, but it's specifically what number? 0. So there's nothing we can test. There's no positive or negative, meaning there's no relative extrema. So there's nothing else we can test. So I'm just going to write out a sad face. More like, what do you want from me? I don't know. The next one, when I plug it into this one, it's going to give me a negative number, meaning it's going to concave down. And when the graph is concave down, it's obvious there's a relative what? Maximum. And the number I plugged in was x equals 1. So when we're looking at this and it's easier for you to plug it into the second derivative test, go for it. If you want first, do that as well. Okay? So let's go ahead and fill in our blank on the bottom. So Milo, let's read. If the graph.
The graph of x is concave of open interval containing c if f prime of c is 0 and fc must be a 1.
So here's your guess. Is it a relative minimum or max? What do you think? Relative minimum? That is true. So I'm going to go ahead and prove that to you with the picture. The graph is concave up. Let's all make a concave up graph. And it's saying there must be a slope that is equal to 0. Is it true my slope here is equal to 0? Yes, it is. And this point, when I put a dot, is that a relative minimum? Yes, it is. It's on the bottom, and it's changing directions. So my second one, Andrew, let's read. If
the graph of f is concave down on an open interval containing c, and f prime of c equals 0, then f of c must be a
relative. What's the other one? Is if it's not the minimum? Maximum. And here's our drawing. Concave down, and there must be a point where f prime is equal to 0. And it's pretty obvious this graph is going up and down, and that is our relative maximum.